Okay, this will be the lecture for Chapter 14, and now we're talking about gases. Now, where we're going to kind of go is we're going to talk about the atmosphere, which is a gas, and I know I talked about it a little bit, but we'll talk about atmospheric pressure a little bit, because this is when the book finally introduces it. And one way we can measure the atmospheric pressure, which is going to be a barometer. Talk about Boyle's law, a little bit about buoyancy in air, and Bernoulli's principle, which is going to be fluids in motion, and then I'll kind of finish off with the fourth stage of matter, which is called a plasma. Now, I want to talk a little bit about how pressure works inside of a gas. So suppose I have a 2-liter bottle or a chamber or something like that, and I've got some gas in there where these green circles are going to represent my gas. Keep in mind that this gas is in motion. These particles are moving and they're bouncing into things. So these guys are pretty much going in random directions. So just kind of draw these guys going like that. And let's just pick this guy right here. As this guy bounces off of this surface, so it's going to do one of those numbers, then it's going to put a force. And that force is going to be outwards, and we call this force pressure. And so this guy's going to bounce off, this guy's going to bounce off, eventually that guy will bounce off, and so on and so forth. All these guys are putting pressure, and it's all kind of radially outwards. Now, not surprisingly, as I increase the temperature of this gas, what I'm doing is I'm going to be increasing the speed. So these particles are going to be moving faster, so this guy right here is going faster, it's going to hit the wall harder, and increasing the temperature is going to increase the pressure of a gas. Now, one form of pressure that we're already kind of familiar with is going to be atmospheric pressure, and essentially it's going to be caused by the weight of the air around you. So, here we are sitting on the surface of the Earth, and we've got, some air right here, some air right here, some air right here, some air right here, all the way up to the very tippy top of the atmosphere. That's a whole lot of weight, actually. And this weight of air is going to put some pressure on us. And one thing to kind of keep in mind is it's going to kind of vary. It's going to kind of slosh back and forth, kind of like an ocean. So this ocean of air that's above us, and it's definitely not uniform. It's going to be more dense right down here near the surface, and it's going to be less dense up here. And it's going to be kind of sloshing back and forth. And the measurements of it are actually very useful. We can predict weather conditions with it. We know that if we have a high pressure system above us, then it's going to be essentially nice weather. And as low pressure moves in, then it's going to be, well, probably kind of rainy. And a really, really, really low pressure system is actually called a hurricane. Now, how much pressure is this for a typical condition? Well, we would say that the typical pressure of the atmosphere is going to be 101 times 10 to the third pascals, so 101 kilopascals, or 101,000 pascals. And that's actually a pretty big number. And I'll talk about the force on the next slide. So let's just take a regular everyday sheet of paper, and it's just going to be an 8-inch by 11-inch piece of paper. How much force should it experience due to the pressure of the atmosphere? And this is a slightly more precise pressure of the atmosphere. Well, we know that pressure is going to be equal to force divided by area. So force is simply going to be equal to the pressure times the area. So 101,325 multiplied by the area, where the area is simply going to be equal to the length times the width. So length is 0.2. The width is 0.3. And let's go ahead and type this in. And we get a force of 6,079 newtons. And as you're, think about it, that's a pretty big number. So the forces are relatively large. And actually I have a demonstration on, the magnitude of the force of atmospheric pressure. So here I have 2 cans, and they're filled with essentially steam. And what I'm going to do is I'm going to put them into some cold water, and you can kind of see that they crush. What happens? The steam condenses, and it leaves a vacuum. The pressure of the atmosphere crushes the cans. So as you can see, atmospheric pressure has a lot of force, and this also can explain how suction cups can work. So suppose you have a glass surface just like this, and you go ahead and you put a suction cup right up against it, then if you just kind of let it hang there, then nothing's going to happen. But as you go ahead and you press this guy into the surface, then what you're kind of doing is you're decreasing the pressure right there, so the pressure is going to go down, and we still have the pressure of the atmosphere. And kind of what's going on is you have these molecules that, they're kind of bumping into it right here. And as we decrease the pressure right here, then you could pretty easily convince yourself that the net force has got to be in this direction right there. And the way that the suction cup is going to work is just a simple pressure differential. Lower pressure here, more pressure here. Net force is going to be in that direction right there, and the suction cup will stick to the wall, pushed there by the pressure of the atmosphere. Here I essentially have some suction cups, and I'm just going to hang from them, so all of my weight is being supported by these guys. What I've done is I've pulled a vacuum inside of that little black thing, and here I'm going to undo it and let you see that I really was hanging simply by the pressure of the atmosphere. So, kind of cool. There we go. Now, as I said earlier, Earth's atmosphere is not going to be uniform. It's going to be the densest close to sea level, so the density is going to be the largest here, and as we work our way up, actually it's going to get less and less and less dense. So you can kind of see that if I were to draw a box right here, I've only got 3 little particles in it. Draw the same size box down here, and I've got a ton of stuff in there, so far less dense towards the top compared to the bottom. And what this also kind of means is if you were to take somebody right here, and as you go higher and higher and higher into the atmosphere, then what's going to happen is you have less weight of the air above you. You also have less of it, and so the density is going to go down, and the pressure is also going to go down. So at sea level we might have 101 kilopascals. As we go up to where airplanes fly, or even to Mount Everest, we're talking about far less pressure, and the very tippy top of the atmosphere, there's nothing above us, so we have no weight above us and no pressure. Kind of applications of this is as you drive up mountains and you go down mountains, then maybe your ears are going to pop. So what's kind of happening is as you go further and further and further up, then the pressure is going down, but the pressure in your ears is what it was at, say, sea level, and when your ears pop, it's simply equalizing out the pressure. Now, one interesting application of atmospheric pressure is it turns out that the highest that a vacuum pump can pump water up is going to be about 10.3 meters. So think about having a really, really, really long straw, just like this, and you were to put some water in this straw, so this guy right here, and you had Superman at the very tippy top. So it's going to be Superman, get his cape going right there, and if we were to be sucking on this and he were to create a perfect vacuum, so no pressure whatsoever, then he's going to be able to suck the water up, suck the water up, suck the water up, suck the water up. And at the bottom of the straw, what we have is we have the pressure due to the atmosphere, and that is a finite number, 101 kilopascals. And up on the very tippy top, we have no pressure. Now, when the weight of this water is going to be equal to the force applied on it due to the atmosphere, then they're going to balance each other out. So that's kind of like a chunk of water, and we're going to have the weight of the water, and we're going to have the force due to the atmospheric pressure. Turns out that limit is going to be 10.3 meters, and since pressure can't ever be less than 0, we can't ever suck it up any higher than 10.3 meters. Now, do keep in mind that mechanical pumps that don't depend on atmospheric pressure don't have this about 30 foot limit. Now, before I move on and I talk about buoyancy, I want to come back and just remind you about Pascal's principle that says if you change the pressure inside of a liquid, then it goes to every part of the liquid. Now we can go ahead and replace this with a more generic fluid, which is going to describe both liquids and gases. So if you apply a pressure onto a gas, it's going to go to every part on the gas. When we talk about how we can measure the atmospheric pressure, well, we have these things called rompers, which are just going to be essentially a glass tube filled with mercury upside down in a dish that's open to the atmosphere. And so here we're going to have some pressure due to the atmosphere pressing down on that, and right up here we're going to draw a perfect vacuum, so the pressure is going to be equal to 0. And what that's going to do is that's going to suck some of that mercury up, and it's going to go up until it balances out the pressure due to the atmosphere. And it turns out that that height for a typical scenario is going to be 760 millimeters, and kind of the old schooly barometers, they actually read how many millimeters of mercury there are. So the height's going to tell us the atmospheric pressure. So kind of what's going on is the mercury column is exerting some pressure downwards, right? This guy right here has got some weight, and that weight is pushing down. The pressure due to the atmosphere is going to be pushing in this direction, but it's going to work its way upwards, and they're going to essentially balance themselves out and support the mercury. Now, maybe what's going to happen as this pressure of the atmosphere, say, goes up, well, the force is going to go up, and so this mercury is going to rise up, and it's going to be at this level right here. Now, applications of this before we had like iPhones with weather apps is if the pressure is going up, then there's going to be great weather. If you're a farmer interested in making hay, then you want to make hay when the sun shines. So if the pressure is going up, great day to make hay. Now, if on the contrary the pressure of the atmosphere were to go down, then this level of mercury is going to correspondingly go down, maybe to this level right here. And if you're a farmer that wants to make hay, this is a bad time to cut hay, because if it rains on hay, it kind of ruins it. So if the level of mercury goes down, not a good day to make hay. Maybe you want to do something else. If the level of mercury goes down to right here, then head for the hills. You have a hurricane coming. Now, you may be asking yourself, how come barometers don't use water instead of mercury? Well, it turns out that water can be used, but it's going to be too tall. So if you think about the buoyant force, it's going to be density, volume times gravity. The density of water is far, far, far less than the density of mercury, so it's going to be far too tall, and actually it's going to be 10.3 meters. Now, you can actually build water barometers, so here's one right here, but really, in reality, this thing's about 30 feet high, so not very practical. Now, something else is we know in cold climates that water freezes, right? And so having a water barometer probably wouldn't be a good idea, because if this thing froze, then, well, it wouldn't be very